Cool. So I think we're recording now. So thanks for joining, everyone. Today with us, we have Professor Archer dialing in all the way from France. He's an associate professor at the University of Rennes, and he's going to talk to us today a little bit about the kernel configuration space. Thank you for joining us again, Professor. Why don't you take it away?
Yeah, thank you. So how can I present? Let me check. This one. Do you see my screen or is it okay? Do you see my screen?
Still loading, but it'll get there.
Yeah.
Yes, yeah, we see it.
Okay. Nice. That's good starting point. Here. Still again? Okay. Yeah, a quick presentation about what we have done, because I'm not alone to do this research, right? And what I think there is a potential to maybe join forces about Clang. So our main idea is that the Linux kernel is an interesting case, right? Because there is lots of configuration options that you can combine with yes, no module values. And it is well known that there are many failures that are due to buggy combination of options, and it's a continuous fight, right, to track and fix bugs. And yeah, our goal is to test the Linux kernel at large scale, a bit like 0-day or kernel CI. And yeah, to give some numbers, this number of options, it's kind of incredible. And so at the end, it's a huge configuration space. And what you typically want to know is whether a kernel build or whether a kernel boots, or what's the size of the kernel, what's the boot time, then what's the performance, what's the security, and so on. But on this talk, I will focus on bugs, right? So whether a kernel builds or not. And it depends on the configuration options you use. And basically, you can succeed to compile a kernel configuration like, let's say, tiny-config or dev-config that are widely used and considered, but some others are not building for some reason, because maybe there is a missing dependency in a makefile, or a bug in the code source in C files, and so on. Especially random configurations that randomly.
Can you try representing? I think most people are only seeing a black. We can see your cursor, but black background, it appears.
Okay. Do you see my screen now? Here?
No, it look. I can see a
Yeah,
cursor.
it's all black.
Yeah.
It's always black?
Yeah.
Yep.
Ah, okay. Sorry about that. And here it's better, or?
It looks the same. Can you try to stop presenting, and then if you relaunch presenting, if that helps?
Yeah, I will try again. I'm sorry about that. I was thinking it was working, right? Okay. Let me check again.
Maybe present the whole desktop, not just one tab. I don't know if you're using just one tab.
One tab. No, I was using the whole stuff. Maybe this one. Oh. We'll try again, but yeah, I'm not sure it's working. And here?
There we go. That looks better.
Yeah, you see the slide?
I see a Chrome window. That's our meeting, it looks like.
No, it's not like what I want. I'm sorry about that, because...
Oh, I think if you switch to a different tab, we may see your slides.
Okay, I will try.
Yeah.
Unfortunately, we're getting black screen again.
Okay. I can drop the PDF somewhere if you want. I don't know if it works or not.
Sure. You want to try emailing it to me real quick?
Yeah. Quickly, right? This one. Yeah, I have sent you just an email with the slides. You should have it now. Yeah. Yeah, it's okay. So you can present yourself the screen and then Oh, great.
Sorry. So if you want to direct me, I'll try to move to which slide you prefer.
I was on slide 3 or 4. 4 maybe. The other way again. Yeah, one step back, sorry. Yeah, this one. So yeah, when you build a kernel, sometimes it's good, right? You pass the test case, I would say. Like you can build tiny config or dev config and stuff like that. But sometimes it fails, especially for random configuration. So at the end, you have some configuration of the kernel that pass, but some other fail. And what we want to know is why there is a failure. So you can have a look at the logs and the error message. But another idea is to track the combination of options that leads to the failure. So that's here we use a bit of machine learning because it's a kind of classification problem when you try to classify configuration in terms of whether it builds or whether it fails, right? And so you can somehow correlate the options with the build status. And then the benefit is that you can identify the combination of options that have led to some failure. So next slide, I will give maybe an example.
Are you using K-test for that, or what do you use to find the combination?
Yeah, so basically we are compiling a lot of configuration. When I say a lot, I'm saying hundreds or thousands.
Mm-hmm.
And then we try to resolve a classification problem when we try to predict which combination of options leads to a failure.
But you don't need to predict. I mean, it's completely deterministic. You need to just narrow it down to one of the options, which takes usually like 10 steps in ktest.pl.
Yeah, but the problem is that, in a configuration, there can be thousands of options, and you don't know which specific option is responsible of the failure.
Yes, but there's like the config bisect.pl script that ships with the kernel. That is what you run if you want to find out which option caused it.
Okay. And then with this script, what are you doing?
Well, you give it a known good configuration and a known bad configuration, and then you tell it to bisect between them and switch half the options on, like switch half the options to what it is in one file and half to the other one.
Yeah, but problem is that this strategy is hard to instrument when you have lots of differences between configuration.
Well, it takes something like 10 to 15 steps. It's like maybe 10 minutes to find to find out what caused the build failure. If you want to do it automated, it's a little slower than doing it manually. So usually when I run into a failure, it takes me something like 2 or 3 minutes to commit a bug fix to my tree and then be off running new configurations.
Okay.
Doing it automated is like 10 to 15 minutes, depending on how fast your machine is.
Yeah, so that's kind of approach. I'm not sure it will work on all cases, but yeah, I can imagine it can work on some case. I think Julia Lawal has developed similar approaches for trying to figure out what can you modify in a configuration to fix it, basically, so that it didn't fail, right? So that's kind of an approach. Ours is a bit different. We don't try to build again. We just have a look at the statistics, basically. So on these concrete examples, we have observed many failures here, and statistically, we can infer that this combination of options here leads to this failure. So statistical learning can automatically pinpoint what combination of options lead to a failure. So maybe you could do that with your script and trying again and again. But with statistics, it's kind of clear. So at the end, we have a kind of table like that with 1 and 0 are value of options, like true, yes or no, or module. And then you have the build status. And then you can infer a kind of pattern that leads to a failure, right? So here in our case, it's a combination of DRM VBox video with generic allocators that leads to this kind of failure. In fact, there are some algorithms, some learning algorithms that are designed to resolve this exact problem. And at the end, you get a decision tree that looks like the next slide. And it gives you basically rules that leads to build failures, right? And thanks to that, you can identify options or combination of options that necessarily lead to failure. So we have done that in the large from some version of the Linux kernel, and we have identified lots of patterns that are real bugs of the kernel, but also sometimes bugs of our infrastructure, because testing the kernel in every possible settings is tricky. So for instance, with the firmware stuff, we have a kind of false positive because it was the cause of our environment that weren't able to support this kind of options. So next slide, maybe. So far,
actually, one comment about that. The first step is usually to enable ConfigCompile Test, which one thing that it does is it enables it lets you enable a lot of options that are otherwise not visible, but it also turns off all the options that are known to cause a build breakage if you don't have some of the dependencies. So if you enable ConfigCompile Test in every build that you do, then you don't run into a lot of the problems that are known failures that will not be fixable.
Okay. So on our previous example, for instance, how would it work on the
well, for the SCSI driver that you showed that needs 68K compiler to build its firmware,
Yeah.
it just doesn't try to build the firmware
Okay.
if you have ConfigCompile Test set.
Okay. But you have to be a bit lucky, right? Because he has to the procedure has to change this specific option. How does it infer this value?
Well, it has a dependency. Like all the options that are known to not build on normal machines, they depend on not compile testing. So you can only try to build them if you're not compile testing.
Okay. But yeah, the combinatorial explosion can be quite important, I would say.
I think another issue
But
is
that's the normal. You still have that problem. It just means you don't run into the 50 problems that other people have run into before and decided that they're not fixable.
Yeah. Okay.
But
And
you still run into regressions. The regressions are the ones that we care about. We don't care about learning about the problems that we already know are there.
Yeah.
I think one of the things that's interesting is you talk about uniform distribution or lack thereof for RAN configs, and it's very difficult with dependencies between the configs, right? Is a RAN config can never truly be random, or at least uniformly randomly distributed because of these dependency chains.
Yeah, that's right. It's interesting problem, right? To have a truly random distribution, uniform, because of constraints. So in the artificial intelligence community, it's called SAT sampling, and yeah, it's not straightforward at all. But clearly, round config in the Linux kernel is not uniform. But yeah, we are using it because there is no better approach, I would say.
Yeah, there's also a problem that a number of bugs only happen if you have a situation where one option is turned on and 100 different options are all turned off.
Yeah.
So each of those might select a symbol, but one of them accidentally does not select that symbol, and then it breaks if all of the others are turned off. And in RAN config build, you never run into this case where all 100 are turned off. But it can still happen if somebody does it manually and they run into a bug that you don't find in RAN config.
Yeah.
I've had one case where I needed something like 40,000 RAN config builds before I found a regression that got introduced by another developer.
Wow, 40. How many? How?
Well,
40,000.
I found it like I'm usually doing like something like 1,000 RAN config builds a day, and I found it after half a year,
Okay.
or no, more than a year. It was like
Okay.
it was clearly a bug. It was a one-line fix. It was just one combination of options that was really hard to hit in a RAN config.
Okay, I see. Wow, that's a incredible story. Okay, but yeah, that's why we are sometimes using statistics to try to find a pattern out of these tries, basically. Okay, tricky case, but okay. But yeah, so we can continue the discussion. But going back to Clang, so we are doing that only with GCC, right? But there is no reason we cannot do that with Clang. That could be the same approach. We use a lot of random configuration with Clang, and then there may be lots of failures, and then you have this issue, right? What the hell is going on? What are the responsible options of these failures? So we believe this statistical learning, this decision tree, can give you rules that group together some failures and gives a possible reason why there is such failure. And then, next slide, it's of course up to the expert, the developer, to know whether it's a Clang specific issue or a real kernel bug. So then maybe an ID, following Nick's suggestion on the mailing list, maybe if we identify a faulty combination of options, maybe it is worth to try with GCC and Clang and compare the outcome, because if it gives the same results, yeah, most probably it's a bug of the kernel. But if it gives different results, maybe it's specific to Clang or specific to GCC, right? So I guess this part can be somehow automated. But at the end, I have impression that kernel developers should be in the loop to at least supervise the process and say, okay, it's a Clang problem, or no, it's a kernel issue. So yeah, conceptually, I think we can try on Clang with a similar approach. And at the end, I have impression that the goal would be to improve the C-Lang support, because we can find cases in which Clang is not doing well on some random configuration that act as test case, I would say. So that's basically the approach. Yeah.
Right. So with my rand config testing, I think we are at the point where we hit roughly the same amount of bugs in GCC and Clang on an x86 build.
Okay.
We hit maybe a couple more bugs on an ARM64. Actually, it might be the same. Like both on x86 and ARM64, there might be a few extra bugs with Clang, but basically they run mostly into the same bugs, and then some bugs that are specific to one compiler or the other. If you build for ARM32, there are still a number of Clang-specific bugs that you run into with rand config builds. And if you go to less common architectures, it gets worse for Clang, but it also gets worse for GCC.
Okay.
Because those are the three architectures that I've been fixing all the rand config bugs for, and nobody else has done it for any of the other architectures, as far as I can tell.
Okay.
And it gets much worse if you try to use the whole Clang toolchain using LLD and the integrated assembler. So that works mostly for x86. It works kind of for ARM64, and it really doesn't work for ARM32.
Okay. Okay. And how do you know that it's a Clang-specific issue?
Well, what I do is I do a lot of rand config builds, and every time I get a warning, I look at the warning and I fix the code, or I open a bug against the compiler. So I have looked at all of them, and I understand the problems. So it's a different approach that requires a kernel developer.
That makes sense.
Yeah, I think it's a very interesting idea for the case of, like, if you have a known good configuration, right, of like we see this even, I think part of LLVM's or the static analyzer has different theorem provers or SAT solvers, and they will, there is functionality built in where, if it detects something, it can do something faster, but it's kind of lossy, and then it can do a more precise analysis to follow up and trim back the results. So, if builds with Clang appear to be faulty, but the same config, appears to work with GCC, that's a good, helpful point. I think the hard part is, one thing that might conflate that is, given a .config, you typically cannot go from a Clang build to a GCC build with that .config file, because kconfig, which runs kind of before the K build, generally you generate a config, will do a bunch of tests against your toolchain and can make it so you cannot select certain configs if your toolchain doesn't support something. So,
right, most bugs I think you can find, because you can just run make old dev config, and that option takes the old .config and tries to pick the defaults for anything else that's different. And if some option doesn't exist, it will ignore it. And if a new option pops up, it will pick whatever is the default. And most bugs you can find, but certainly if some feature only is supported for one compiler and then it breaks, and that feature doesn't work at all for the other compiler, and we turn it off, then you wouldn't find it.
Okay, I see. But
cool.
Yeah, basically you need to migrate the .config file, right? So with all dev config or with some heuristics, basically.
Yes. So all dev config is probably better than any other heuristics.
Yeah.
Unless you already determined that one of the options causes the problem on this one compiler, and the option goes away if you move to the other one. In that case, you know what's going on. Like it makes sense to have a check for that.
Cool. Does anyone have any other questions?
So have you considered doing some like avoiding the known broken configuration. So if you determine that the combination of 3 options breaks something, and you do a new random build that you just and that you run make rand config, and you get the .config file that you know runs into this problem, that you just skip that, or
yeah. So that's one of the motivation as well, is to have a kind of temporary fix to avoid configuration for which we will know anyway that it will fail. So we can save some budget here and avoid recompiling some buggy configuration.
Well, it's more about the case. So what happens sometimes is that one option is always broken, like one driver breaks,
exactly,
and then half the config files are broken, and then you just don't need to test it again.
Yeah, so that was our experience. Actually, we find 3 options like that breaks lots of configuration, but with statistical learning, we can prevent this failure because we know that it will anyway fail. So we deactivate some options a priori.
Yep. Good.
So, yeah.
You use a .all config file, like a kconfig all config file, or do you use something else?
So we are using a run config with some preset options.
Right.
Yeah. So that was our trick. It works pretty well, and it allows us to save lots of budget.
Yes. So in those preset options, that's where you should also set the ConfigCompile Test equals yes.
Okay. Yeah.
You should also set config debug info equals no. That will dramatically speed up the builds. Like half the time you add debug info, and it never causes problems, but it just makes the linker slow.
Yeah, that's interesting trick. Okay, I will get back to you for for having this kind of hacks. It's interesting. Yeah, thank you.
So I think there's I feel like we should probably meet again and talk more, because there's probably a room for a lot more discussion on the topic. Thank you so much for dialing in. For kind of updating your presentation for us. We really appreciate it, and I think we all see a lot of potential with this research. It's very, very valuable.
Feel free to write to me personally if you have questions and other things, or want to talk again.
I'll try to.
Thank you very much.
Yeah, I'll send out the slides and hopefully the recording if I should be able to find it.
No problem. You're welcome. I will attend as well the second session.
Cool. All right. So next up, kind of common feedback that we've gotten from kernel developers is really, kind of the faster the code compile, link, build, test step is, the more development that we can get done. Right. I think focusing on compile times, build times in general, is something that improves developer velocity and allows us to develop features faster. Right. And I think part of having a tool chain that's worthwhile is one that gets out of people's way and really is something that they don't have to worry about. And we certainly have a lot of work to do there on multiple fronts. But Nathan Huckleberry, who is a undergrad computer science research student at University of Texas at Austin, is an intern at Google this summer and is looking into instrumenting Clang and LLVM itself. That way we can start kind of profiling and finding, where are we spending time when building kernels. And he's kind of focused on, measuring Clang's ability to build the Linux kernel, which I think is special because, it's not really focused on C++ code, which I feel like a lot of other Clang developers are kind of focused on. So, thanks again for doing all this work, Huck, and go ahead if you're ready to present. It's all yours.
So there was some discussion about Clang versus GCC compile times, and in an effort to determine why Clang is slower, I've instrumented Clang with Perfetto, which is Google's replacement for Chrome tracing. So when you run Clang with this Perfetto flag, it produces a trace file that has custom trace events that will come up in the Perfetto viewer, and you can go through and look at where we are spending time compiling stuff. So This is a compilation of just an arbitrary kernel source file. I just picked one at random. Like you can click on the source on these slices and you can see like down here, this is including this header file. And you can like click on these optimization passes and see what function is being optimized here. And you can click on like the actual pass and you can see the name of the pass itself. So these trace files, you can make shareable links for them. And when you send somebody one of these links, they just open it and they get the exact same view that you have. There's a query engine that you can use to basically do analysis on your trace. So here we see we're spending 2,400 milliseconds in the front end, 3,700 in the back end. And what's really nice about this is you can concatenate these traces together with just Linux cat. So if you do a build of the kernel and you take all these trace files and you just cat them all together, you can get something that looks like this. And you can see all of the translation units together, and you can do queries on these as well. So these are in seconds now because they got really big, but we spend 2,500 CPU seconds in the front end and 600 in the back end. And same thing with these shareable links. Pretty useful. I haven't really done too much analysis on the actual traces themselves. I've mostly spent the last 2 weeks and up to like 30 minutes before this meeting getting the tracer to work. So yeah.
So is this a live demo or is this
This is with the most recent changes that I've made. This is essentially what I'm planning on posting to Fabricator.
Great. So it sounds like
what kind of changes do you mean? Did you make changes to the kernel or to the compiler or both?
To the compiler.
Okay.
So I've had some amount of issues with getting Perfetto to work, just in general. Like these slices are actually like limited based on slice size. So if the slice is not larger than 2 milliseconds, it doesn't get recorded. And I've had quite a few issues fixing that. So now everything seems to work. But yeah, it's just changes in the compiler with the actual tracing.
Nathan, can you give a little bit more details on how did you instrument the compiler for this?
Yeah. Here, I can actually pull up. So so Perfetto itself exposes like the C++ API. So you link it with, you link the Perfetto library with CMake. So here's the CMake commands that I've added. So it pulls the Perfetto GitHub when you build, and then it automatically links it everywhere that it needs to be linked. And then there's some macros that were defined in the compiler. And whenever you want to record a trace event, you just do like LLVM trace. And yeah, you just call this LLVM trace macro, and it will record your trace through Perfetto if you have Perfetto enabled. And then to build with Perfetto, you have to pass a CMake configuration flag to your CMake command. So you'd have to do like -d Perfetto when you're building Clang.
And what is it that you are tracing? The different starts and end of phases or what? Or
yeah, so there's 3 different macros that I've added. One is here. Let's see if I can find it. I don't know exactly where they are in here, but you can do like LLVM trace scope, which creates like an anonymous struct, and then when the struct goes out of scope, it ends the. So it creates an anonymous struct, begins a trace event, and when the struct goes out of scope, it ends the trace event. And then there's also LLVM trace begin and LLVM trace end, which are just explicitly beginning and ending trace events. So most places just use this LLVM trace scope because it's more reliable than the LLVM trace begin and LLVM trace end. But yeah, you would just add like an LLVM trace scope macro anywhere that you wanted to have a trace in the anywhere you'd want to have a slice in the trace.
So Huck, I'll add some rhetorical questions for purposes of the reporting, but how does this differ from LLVM's -FTimeTrace or -FTrace report?
Yeah, so LLVM-FTimeTrace does essentially the same thing, but for Chrome tracing. So first of all, the traces are smaller. In my limited testing, they're about 3 times smaller. As well as you can concatenate these traces easily. With the FTimeTrace, you have to do some magic and like actually parse through the file to concatenate them. With this, you just run cat. There's also the query engine that the LLVM FTimeTrace does not have, and then shareable links as well.
Cool. And with this instrumentation infrastructure in place, what do you think are the next steps for us to start investigating improving compile times with Clang for our Linux kernels?
Yeah, I think some time needs to be spent going through and actually doing analysis on these traces. I haven't really looked into what's going on at all, but currently it seems a bit suspicious that we spend like 5 times more time in the front end than we do in the back end.
Does anyone have any guesses why that might be the case?
Yes. So I just spent the last month on and off looking at improving compile speed of the kernel by reducing the header files, and I'm now at like over 30% improvement with Clang 10 just by reducing the number of header files that get pulled in. And we found earlier, like many times before, that there's one significant difference between the way that GCC and Clang look at files. So GCC, one of the early things it does is that it identifies dead code and completely throws it away, and then it doesn't report any bugs in that code that it would otherwise find, whereas Clang does a lot more processing on all the functions that are visible and then does dead code elimination much, much later. And there's syntactical analysis and all that, and like tracking uninitialized variables, whatever that does just for reporting errors, that is certainly useful. But I suspect there's also a certain number of optimization passes that happen on unused functions that are then thrown away.
I would also guess GNU-C statements probably cause a lot of that as well, because I know that just came up recently with like the KC sand macros and stuff of that nature.
No, I think what happened there is that we pass a statement into a macro, and that statement contains another statement that is expanded like a few times, and then the second macro expands it another 8 times. it just explodes. So a single line of code can turn into thousands of tokens.
Yep.
Right. In the case that Nathan's referring to, Clang basically spends a lot of time trying to accurately track what the source location of a given token is when it comes to macro argument expansion for the purposes of reporting diagnostics if there's a warning or error to be emitted. And in that case, there were some kind of pathological cases, where maybe traditionally macro argument parameters are only a few tokens, but in the case of GNU-C statement expressions can be, almost entire function-like kind of macros, which have many, many tokens to be expanded, kind of thing.
So one
For the particular case, I noticed that like the average preprocessed file size grew from like 4 to 6 megabytes to 30 to 40 megabytes. And I've got it down to like 1 megabyte now with my changes on the kernel.
It's hard to imagine 30 megabytes of input source, but that's only C code. I can't.
That's just header files with inline functions that are never called.
I've actually seen similar cases before. Like, I've run into cases where just changing the order of passes actually, affect the build time a lot. It's similar to that code elimination. So I ran this man to reg pass on LVM to remove some like useless stack variables, and then run some optimization. It actually, improved the build time a lot. So I wonder if that's the case like here. But like if you want to look into improving build time, that might be one thing you can look at, is to change like the order of optimization passes.
That's a great idea. We always had these discussions of, optimally you would run dead code elimination after every pass, right? A lot of passes can kind of leave behind garbage, and they kind of rely on DCE to clean up after them, which kind of results in like garbage being re-optimized again and again and again, which is tricky. So I think, having these links, like to me, it's like Godbolt, right? Where you can just share the link is incredibly powerful, because suddenly now we can make changes to LLVM where we either reorder passes or maybe we remove passes from the O2 pipeline and say this is only run at O3, and actually quantify and show like, here's an entire build of the Linux kernel. Here's how much faster it is, with or without this change, kind of thing. Being able to quantify things is a very strong argument.
So what I'd like to see is an optimization pass, and that basically just looks at static functions and sees if they are called at all, and then throws away the entire function before we do any other optimization passes. But after, of course, checking that there are no syntactical errors in that function. And that would get rid of most of the contents of those header files. So if we can just free up all that internal state and then start the actual optimization, that might make a huge difference.
So we'd want something like that to run before semantic analysis if we're spending a lot of time in semantic analysis on dead code kind of thing. And there's kind of whisperings, actually. I feel like so like Chris Ladner created LLVM, and at least 2 cases I can think of where he has these kind of shallow digs at Clang itself are his 2015 presentation on Swift and kind of the design of Swift's IR, but also some of his MLIR talks. They actually talk about, how could Clang, move to using MLIR instead of LLVMIR. And he actually has concrete suggestions where he talks about with Clang, like he kind of points to this asymmetry between, Rust and I think maybe Julia and Swift all having IRs kind of before LLVMIR that are more specific to the front end language. And he kind of points to this asymmetry where he says Clang does not. And he says if Clang did, then we could base code gen on control flow analysis instead of doing an abstract syntax tree walk. And at that point, the control flow analysis kind of gives us that information that like this function is entirely unreachable, right, in the front end. And So, I think things like that are like, wildly different architectural changes that will take years to do in Clang. But, I think it seems like we understand pretty well now, a major pain point is the semantic analysis of dead code. And in particular, that's one of the reasons why we still can't build a 32-bit x86 kernel quite yet. Is there's very interesting kind of metaprogramming going on, with some macros that make use of GNU-C statement expressions and use type of quite extensively for kind of it's an interesting form of polymorphism kind of thing, but the hard part is it's really kind of tightly coupled to GCC's ability to throw away kind of dead code before semantically analyzing it. So we have some cleanups there, but there's more work to be done, kind of thing. It certainly is a little tricky, and thankfully we don't have that issue today with other architectures, I think. But I always worry that those could creep back in. So. Awesome. Thanks so much for all this work, Nathan. And we look forward to your RFC this afternoon. And I guess I'll send the meeting notes maybe after that RFC goes out. That way I can send everyone a link that as well. And I look forward to playing with this, and hopefully we can find some interesting and fun, curious bugs. So thank you.
So I do have a quick question. Like, does GCC have similar tool? So like, if you can find a similar tool for GCC, then it's probably easier for you to look at the differences and figure out where we can improve the most on Clang.
I don't think that they do. So on the original FTimeTrace commit, I remember seeing like some GCC maintainers saying, "I wish I had this for GCC." I don't know if they've implemented that, but that seems to indicate to me that no, they do not.
Okay, right.
I mean, it's always hard to build a tool that will be generally useful to people. I think if we can show that this is an actual useful tool that people can then go and make important optimizations from, this is something that we absolutely should share with GCC developers and show like kind of what's our workflow for addressing these problems, kind of thing. Because I'm sure they have very similar issues that Clang does, right? And performance cliffs that people, it's very hard to understand. This looks like such an innocuous change. Why am I getting such drastic change of behavior?
Agree.
Cool.
I have a question. Is it possible? Yeah, I was wondering which configuration do you use for running your experiments?
This is just with x86 64 def config.
Okay. And do you think it would make sense to change the configuration to see if there is other insights we can extract?
Yeah, probably. I haven't really done any actual analysis with it yet, though. I've literally just been trying to get the tracer to work up until today. So now that the tracer works, actual analysis can start.
Yeah.
I would guess that if you can get some results for def config, the next step would be to try it again for x86 all mod config, which has a number of options enabled that can make a huge difference.
Yeah.
Rand configs probably don't make sense for a while until you have like actual until you have changed a lot of things based on the first findings, and then you can start looking into others. Doing it on other architectures, of course, like building a ARM kernel instead of x86 also makes a huge difference. So especially ARM32 seems to be much slower than ARM64 and x86. So there might be something specific to ARM32 that makes that particularly slow, whatever that is.
Yes,
could just be that the headers are bigger.
In particular, one thing that's a little tricky to tease out is not only do different target architectures have different kind of source files, different def configs, different sheer amount of lines of code we're throwing at the toolchain. But then what further complicates this is the toolchain itself will have different pipelines based on the target architecture and the optimization level. And so it's absolutely possible that, like LOVM, for example, has 3 different register allocators and 4 different register allocators and 3 different instruction selectors. And which one is used? Like, they're radically different architectures with wildly different performance characteristics and generated code performance. And they're kind of mutually exclusive. And it could be that different architectures are using wildly different combinations of these kind of thing, which can kind of conflate that further. But having the analysis, absolutely is kind of the starting point. I think before having any like hypothetical discussions, being able to measure is kind of the most helpful kind of thing. So cool. Do we want to go over any other status updates? I realize today's meeting is a little bit longer, but I was very happy to have more discussion on all these talks kind of thing. Otherwise, we'll cut it here. Cool. All right. Thanks for your time, everyone. Thanks for our
Just really fast, is there anything that you want to discuss as far as the plumbers proposal is concerned?
Yeah, so I can give a quick update about that because at least Nathan asked me.
And I've talked directly to Steve about this as well.
Cool. So yeah, I think your feedback was definitely helpful, and we got some more feedback from the MC chair, basically saying like a lot of the current proposal was either too generic or too specific. But then they also wanted like a list of speakers and like a confirmed list of speakers and like a commitment of who's going to be there kind of thing.
Exactly.
So those things.
Incidentally, the MC chair is Steve Rostat, so he's the fellow I talked to directly. That's essentially why he got back to you when he did, because I poked him a few times.
Mm-hmm. So I think we could probably do like an RFC on our mailing list to see, does anyone have a proposal, a concrete proposal that they'd like to give. Right off the bat, I think LTO probably could definitely have its own meeting for that kind of thing. I think there's some contention around do we need to worry about memory ordering here or not kind of thing. So I think that seems to be something like right off the bat that's interesting. I think we can give proposals about things like auto FDO and PGO and LTO and like try to show some numbers and say like we have patches for these things. Like I constantly am arguing about carrying anything downstream or out of tree. To me, it's all technical debt that I don't want to carry or pay for. So, kind of setting the discussion of like, these things exist. Things like Rust in the kernel is something that like I have working, but there's a bigger discussion around, do we want this and what are the implications of that? That might be interesting.
Basically, anything that will start an argument is the right topic.
I feel like
Mark, that's true.
I feel like I really don't want to. You're like anything that will involve walking into a meat grinder, you should willfully sign up to do. I'm like, yeah, I don't really want to do that. So I think we should humor the MC chair, and I think we should put together, maybe something even more concrete than.
Just bear in mind that some of the worst bugs we had at the very beginning of this were solved at Plumbers, and it was because essentially we had the right kernel people come to the conference. I mean, for instance, one of the changes we had to David Miller's code that we couldn't get him to accept, Dirk and Linus showed up, and we basically proved there was no other way of doing it, and basically it meant that we could send our code directly to Linus, and he submitted it. So this is for all the roadblocks. When I say the argument, I mean that in the nicest possible way. As much as Mark is smiling again, as much as there are near fist fights sometimes in these talks, that's not what I'm talking about. What I'm saying is that the more you can get people basically discussing things openly, where there's usually conflict on the mailing list, if you can do it live, a lot of things move very quickly at Plumbers. So.
Yeah, I mean, I'm definitely disappointed that the conference is going to be virtual. I think that's absolutely the right decision. But the thing I really will miss is just in-person hallway conversations are always extremely valuable about Plumbers kind of thing. And I worry, I don't know if they're going to provide a alternative forum for things like that. But
they're using Big Blue Button, and they are thinking about that very problem right now. So yeah, no, there will be something like that.
Yeah, they like trialed using it for discussion at the town hall thing they did last week.
Yeah.
Which I missed it, but some of the people I know who were there were saying it was working pretty well for discussion. So, yeah, I mean, they've already had to deal with issues of multiple people talking and technical stuff because of the recordings. So I'm not sure it's actually going to hurt it as much as all that for the in-room discussions to have it online. Obviously, like you say, the hallway track is going to be out the window, but hopefully at least people can follow up from a discussion that happens in the room.
Yeah.
What they're doing at ELC is they're actually running, and I'm not suggesting we run Slack, but they're running a Slack for all the hallway track stuff. It's working pretty well. So I imagine if there's a matrix server alongside Big Blue Button, that it'll work okay. But honestly, during that town hall, we had everybody talk at the same time, and we tried all the failure modes, and it worked really, really well. So basically, I'm pretty sure it's going to work okay.
Yeah, I as frustrated with as I am with, I feel like it's I feel like we're being asked to jump through more hoops. But I've had to deal with red tape in the past, and the alternative is not making an appearance. I don't think is a good idea because
they want you to succeed, Nick. This is making it better. This is not a red tape thing. This is that they wanted to succeed. Yeah, stop smiling, Mark. They wanted to succeed, and they want. Steve really pushes for this every year. So basically, as long as it fits the format appropriately, you're in with a charm. There's no problems. It just has to fit what they're looking for.
Yeah. Cool. And then I guess after that, I think it might be interesting to get some folks giving some talks at LinuxConf AU. I've been interested to attend that. So, well, I'm asking everyone to keep an eye out when the call for papers comes out for that. Let someone know, right? Let our list know, something like that. So, cool. All right, we'll cut it here. Thanks for your time, everyone. See you in 2 weeks.
Thank you.
Thanks, guys.
Bye.